the sludge. Now it's just crystals in the sludge.
How much of the magnesium are we gonna have to dose it with?
Say again?
How much of the magnesium are we looking at to dose it with?
I don't remember.
It's looking like probably 30 or 40 milligrams per liter. But it will depend on the testing that occurs once we're actually producing biological phosphorus sludge and digesting, which we don't know what that's going to look like yet.
So struvite is a usable form of phosphorus, like?
Yes, it's used as a fertilizer.
Okay.
It's bad on your belt presses, it's good in the sludge.
Yeah, that is a
It's like taking aspirin. It's great for curing your headache. If you take too much, it will kill you. So, struvite can be good or bad. Oh, and that's just a relative sizing. Actually, it's interesting, this picture's taken in Germany, and you can see the egg digester in the back. So it's going to look something like this here. So last topic then, side stream nitrogen removal. Remembering that about a quarter of your ammonia is in the side stream going back to the headworks. This won't take long for those who need to talk. This shows the A-frame construction of your nitrification and denitrification reactions. You go from ammonia to nitrite to nitrate, and then back through nitrite to nitrogen gas. There's some approximations for the amounts of oxygen, relative oxygen required, and the relative amounts of carbon. And if you can, the research over the last decade has shown that you can shortcut this process so that you don't have to go all the way to nitrate by controlling the dissolved oxygen concentration. And so some of the earlier forms of side stream treatment cut it off at this point and went to nitrogen gas from nitrite. What it does, it saves this amount of oxygen and this amount of carbon by using this split flow technology. The sort of rage today is the use of Anammox bacteria. It's an acronym formed from the full name anaerobic ammonium oxidation, which is the process that they implement. And what it is the fact that you operate a system with alternating aerobic and anaerobic environments. So in an aerobic state, you take the ammonia, oxidize it as far as nitrite using the AOBs, and then you would take the nitrite, turn the air off, and then this wakes up the Anammox bacteria, and it'll take a molecule of nitrite and a molecule of ammonia and reduce it to nitrogen gas. This is literally one-stop shopping because you've eliminated all of this other stuff in gray. You saved all of the carbon, it's totally gone, that demand has gone away, and you've eliminated a large proportion of the oxygen required for ammonia. And it has a couple of other advantages. The biomass required is much lower because the yield of that anaerobic organism is pretty small. And it also reduces the amount of CO2 emissions because of the reduced amount of oxygen required to carry out the nitrification process. So I want to just to quickly illustrate, this is new for you, so it's a little graphic I put together where in the Anammox system there's 4 different kinds of organisms. You know from what you've seen already that there's AOBs, there's NOBs, there's the heterotrophic denitrifying organisms, and there's these new guys on the block, the Anammox bacteria. Now, they all have a problem with each other because in order to grow the Anammox bacteria, we have to freeze out the NOBs and the denitrifiers. We need the AOBs to work because that generates the nitrite. So it turns out that the high concentrations of ammonia that are present in the dewatering stream, they inhibit the growth of the NOBs. So that gets taken care of. But these three organisms here, the Anammox, the denitrifiers, and the NOBs, compete for nitrite. Well, we've just eliminated the NOBs, so now we have to figure out how to freeze out the denitrifying bacteria. So the denitrifying bacteria are favored by low DO, but the Anammox bacteria are favored by no DO. So now it becomes critical that we control the Anammox reactor by having 0 DO during that cycle, that part of the cycle. So we freeze out the growth of the denitrifying organisms. And so there's a lot of stuff going on in there, and this is, if you like, your first introduction to Anammox bacteria. They're the coolest technology out because they do everything that the nitrifying, denitrifying organisms have done for the last century of wastewater treatment, and we've eliminated it in one fell swoop. It's literally one-stop shopping. But there's a lot of intricacy in terms of keeping the Anammox bacteria in operation because of the inhibition of its growth by these other 3 sets of organisms which are in competition. So we'll come back to this later. So you've seen some of this before. Commercial Anammox processors are 3 types: suspended growth, fixed film, and granular. And the best example of the suspended growth is something we call the Demon system. And the red color is kind of interesting. If you recall, the demon is red, isn't it? It's demonic. So I think it was a very clever marketing selection of names for the technology. And this shows a pilot unit that we operated up at Pierce County. There are 2 plants in the U.S., one in Canada now, which are operational. There's almost 40 in Europe. So this is by far and away the most widely applicable or applied technology for nitrogen removal in side stream. It lends itself to an SBR configuration, and you can see the micrograph here. These are granules, sort of small granules, and they're close up. They look like the chocolate sprinkles on your ice cream in terms of size. And we try to control them through the use of hydrocyclones to separate the heterotrophic organisms you don't want, the denitrifiers, and we keep these granulated organisms because they're heavier and more discrete through the use of a hydrocyclone, just like you use it for grit removal. You separate the denser particles, the sand particles, by using the hydrocyclones. Very similar type of operation. And then we use a system of pH and DO settings to control for the Anammox bacteria to be retained and discourage the growth of the other 3 sets of organisms. Does anybody know how an SBR works? Maybe not. So maybe this is irrelevant to you. We go through a period where we aerate an aeration tank, and for a period of time, and then we turn the air off. The DO disappears. That creates the environment for the Anammox bacteria to kick in, do its thing, and then we add a little more substrate, the return stream, turn the air back on, you make nitrite, you turn the air off, and then you induce the growth of the Anammox bacteria again. And so it keeps going on and on and on like that until you fill the SBR, and at some point you turn everything off, the sludge settles, you decant, and that's your deammonified return stream, which is then sent off to the headworks. So in essence, that's what this blue line illustrates, is the on-off of the aeration. You get up to a certain height, then you let it settle, you decant, and then you start the whole process again. It's potentially the process we may use here for the nitrogen control of the side stream. The alternative would be something called Anidamox, which you use the same bacteria, but they grow as a slime on these little plastic media, which are no bigger than, say, 1/4 inch diameter. Next time I'll bring a few examples for you to see. But essentially, we do the same thing in a fixed film as we do in a suspension of organisms. This is the plastic media, a cartoon representation. Biofilm grows. On the inside, there's not much air, so the Anammox bacteria are going to grow there, and the nitrifiers grow on the outside. So the ammonia diffuses through the first layer of biofilm, is nitrified by the AOBs to nitrite, and the rest of it continues to diffuse to the Anammox film. The Anammox addresses one molecule of ammonia and one molecule of nitrite, forms nitrogen gas, which then diffuses out of the biofilm. And it's exactly the same process as in the Demon. It's just that you grow the bugs in a different fashion in the form of that biofilm. And you can use different kinds of media. You put them in a reactor, and you have to put screens on in the overflow to make sure you don't lose these tiny little plastic media in the overflow. And then the last type of reactor is something we call a granular reactor. And there's a micrograph of what these things look like. These are larger particles than the Demon system. They're maybe about 0.3 to 0.4 millimeters in diameter, and these literally settle like rocks. What's shown here is a comparison of a regular mixed liquor after 5 minutes of settling. Typically, you'll see the interface form and maybe 5 or 10% of settled volume, or supernatant, should I say. Whereas in the same 5 minutes, these bugs in a granular form settle right to the bottom. Boom, it's that fast. So this lends itself to a very tall vertical reactor, which is great from a footprint saving perspective. And they have these unique passive gas, liquid, solid separating devices. This is really cool technology invented by the Dutch. And so you can really push through a lot of flow in a small diameter, which is why these reactors are tall and thin, and achieve the same level of efficiency that the Anidamox or the Demon process can in squatter, fatter sort of reactor configurations. So I guess I'm going to leave this up here just to see what questions you may have, if you have any at this stage of the game, or if you want to go home or whatever. But you know, what does it mean to us, just as a starting point? That piece in the middle, your trickling filter, solids contact tanks are all going to get, well, actually the solids contact tanks are going to be repurposed, but the trickling filters will gradually be replaced, not repurposed, replaced. Anybody have any, oh, and then we'll have the fermenters, we'll have the side stream treatment technology, systems installed. be a few changes on site. Anybody have any thoughts about what they think of the whole deal here? A lot of change coming.
With the Animox process, is there much need for carbon or the readily biodegradable carbon? Just
Now, if you remember, I guess I screwed it up, the little A-frame chart that I showed.
right.
It shows the illumination on that whole side on the front, on the right-hand side.
Right.
The carbon. The carbon out there.
Is it a size problem? Don't we do that for waste?
We can inhibit the growth of the NODs when the ammonia solution, when the ammonia is so dilute that 15 milligrams per liter. Yeah, that's why it works so well inside stream, because you've got several hundred milligrams per liter.
There are a few people playing with things.
I guess everybody's had it, is that right?
When's construction start?
Huh?
When does construction?
3 years.
3 years?
Total cost we're looking at? Cost, how much we're looking at?
90 to 100.
Million?
A lot of money.
How long will it take
4 years.
to construct?
How many basins are we looking at filling up here?
Well, initially, it'll be,
Like 4 to 5 trains,
Wow.
well, relative to,
1 and 2.
I don't know if you remember, but we showed these in the last set of slides, which gives the first phase of installation of the aeration tanks on top of the trickling filters. So that'll be, and they'll be coupled with the existing tankage that you've got up there with the solids contact tanks.
Will we demolish all trickling filters, including the
Yeah.
ones on the?
Way in the future, yeah.
Yeah, they'll all go.
Well, the first phase is only going to take out the ones on the west side. The ones on the west side will be the first to go, and then the ones on the east side will be retained for quite a while until the state finally passes the
No,
final.
the ones on the west side will get demolished right away to the aeration basins, and well, those are constructed, we'll need to operate the east side filters.
Right.
And when the aeration system gets up to speed, then we'll demolish the east side.
Basically, all of our flows is gonna go to the east.
What?
Get out of the way.
No, we're gonna,
Well, the problem is.
we're gonna get our activated sludge going, and then we're gonna demolish it.
East side.
Go through all this, we'll have to maintain our MPD estimate as close as possible, or?
Yes.
Of course.
Yes.
Yeah, this is the big challenge. That's why we're starting the training earlier.
Yeah.
So you start to get familiar with the terminology and the concepts so that it doesn't come like a red brick sort of